Well, good afternoon. Here, my name is Mark Laurie. I'm the superintendent of schools in Niagara Falls, and I wanted to just say welcome and hello, and we're glad you're with us. We have a really outstanding presentation for you over the next hour, and I guarantee, as you see the microphones here, that you'll be able to ask questions. But I'm really pleased and proud that you came out to meet Astronaut Hansen today, and that you're part of us with us at Niagara Falls High School. I just want to acknowledge and welcome our mayor, Mayor Robert Rustino, who's here. Welcome, Mayor. We're glad you're with us. Mayor will not be taking the trip to the moon, just in case anybody was interested. He won't be taking the trip to the moon, but we're glad that you're with us, as we are all of you for being here. So it's really my honor to say hello and welcome, but most importantly, to introduce one of our Niagara Falls High School students who has the honor of introducing our guest today. And it's so appropriate and so nice that Madison Simpson is here, who in a moment is going to introduce our guest, because Madison typifies what a Niagara Falls High School student is, and she takes it to another level. Madison is a senior who will be graduating in June from Niagara Falls High School after spending her whole academic career at High Park Elementary School and then LaSalle Prep Middle School, and then for the last 4 years coming to Niagara Falls High School. Madison is an outstanding student. As a matter of fact, the April 16th, when the district holds its Dr. Martin Luther King a celebration to honor community members and one student, Madison is going to be the recipient of the Martin Luther King Civil Rights Award for her work. So, she is an impressive young lady. Madison, future plans are to go to college, either at Howard University or Morgan State, where she will, I'm glad you're cheering that. Where, get this, she'll study math and physics. So it's pretty impressive to have Madison here. And we thought that it would be most appropriate for her, one of the great Niagara Falls High School students and one of the great individuals that we have, to introduce our special guest. Madison, congratulations, good luck, and the floor is yours.
Good afternoon, everyone. Thank you for coming. Jeremy Hansen is a Canadian astronaut from London, Ontario. He has a Bachelor in Space Science and a Master in Physics from Royal Military College of Canada. He will be on the Artemis 2 mission. Jeremy Hansen was raised in the farm in Ontario, Canada, and has been passionate about aerospace from an early age. His time in the cadets from the ages of 12 to 18 prepared him to enroll in the Royal Canadian Air Force, where he became a CF-18 fighter pilot in several squadrons. Colonel Hansen was selected as an astronaut candidate in May 2009 and got assigned as a mission specialist on the Artemis 2 mission in April 2023. He will become the first Canadian to ever venture the moon.
First challenge of the day, find the microphone.
Hey, good afternoon, everyone. Great to be with you. Madison, you ran off. I wanted to thank you for that, but that was a great introduction. Thank you for that. We should probably just let Madison stay up here and tell us a few things. I talked to her earlier. She's super sharp and probably be part of our future, some cool learning that she's going to do, helping us understand the universe. I thought that was really neat.
Special for me to spend some time with you today. Thanks for sharing it with me. Annie is going to help me with the slide. She's in the back, also from the Canadian Space Agency, but we can go to the next slide. Thank you. Nice of the moon to create this great event for us on Monday to block out the sun so we can see and experience some cool things. I have never experienced a total eclipse before. Have any of you? Raise your hands if you've ever seen a total solar eclipse before. If you didn't see that, some kids put up their hands and their mother put them down for them because no, you haven't. You're not old enough. We know that's not true. But anyway, I'm excited about it. I've never seen a full or a total eclipse before. That'll be really special to witness that. Hopefully we'll have some great weather. But when I think a little bit about the eclipse, it makes me ponder humanity through time when they observe this. I mean, we know that for thousands of years, people have been observing these eclipses. What did they think was going on? And what was their perspective of the solar system, the universe? It just makes me ponder. And of course, with science now today, we understand what's going on here. But as Madison and I were talking about earlier, the more we learn through science, the more questions we have. And so, like simple things, we know the sun is there. We know we survive here because of the sun. But there's still mysteries surrounding the sun, and this eclipse gives us a unique opportunity every time to study it and learn more about it and how it affects space weather and all of that space infrastructure that you and I are using every single day, how it affects that and how we can continue to evolve that technology. So anyway, lots of neat stuff will happen on Monday. Science and learning for all of us. Next slide. My life did change a little bit a year ago when I was assigned to the Artemis 2 mission with my crewmates, Reed Wiseman, Christina Cook, and Victor Glover. The four of us have been really busy with a huge team of people getting ready to send humanity back to the moon. I will tell you a little bit more about the Artemis 2 mission as we go along. But one of the things I want to highlight is this international collaboration and how special I think that is. Next slide. So Artemis, we're on Artemis 2. Artemis 1 was an uncrewed mission, and this is a real image from Artemis 1. This is the capsule down in the corner. We have these neat cameras on the ends of the solar arrays that allowed us to take pictures of the spacecraft, and this is obviously one taken when the spacecraft was out by the moon. Next slide. We are up to big things as an international collaboration because we have set big goals. And I would just like to highlight the fact that I'm super proud of the United States and the leadership example that they are providing by setting a big goal and inviting other countries like Canada to play a role, to contribute to this. Could the United States go to the moon alone? 100%. Already did it. But the United States has deliberately chosen to create space for other countries around the world to be part of this. And by leading like that, we will be able to do more together. And that's a really significant accomplishment. And that will hopefully be a shining example and an inspiration for all of us around the world to just remind ourselves we can do better on this planet. We can learn to create and cooperate, and that is how we will thrive. In fact, I was inspired by an image like this as a child. I came across it in Encyclopedia A. Encyclopedias were these books we used to have. And before the internet, you couldn't just go to the computer to learn, you had to learn in books. And I went to Encyclopedia A, where all the A stuff was, and airplanes was in there. And I really liked airplanes as a kid. I don't know why, never been in one, but I was really excited about airplanes. So I would go to Encyclopedia A and look at the pictures of the airplanes. And one day I flipped to Armstrong, just by accident. And I saw a picture like this one, and I thought, wow, that's crazy. Human beings left Earth, went to the moon, walked on it, and came back. And it just flipped a switch in my brain, and it inspired me. I started talking about, I would like to be a space explorer. Next slide. And so, oh, sorry. I didn't realize you'd switched already. So I did something very, very intentional. Well, no, that's not true. It was very unintentional. But now I realize it should have been intentional. I set a goal that I wanted to be a space explorer, but then I did something very, very important. I shared it with other people. Naively. But because I told other people what I was trying to achieve, when I look back at my life, I realized that it was because of them that I was able to carve a path towards achieving this goal of becoming a space explorer. So in life, it's important that we set goals. They don't have to be career goals, but they could be 1 month goal, 1 year goal, but we should set goals so we know where we're trying to go, and then we should share them with other people so they can help you achieve what you want to do. And that is what we're doing in the space program. We're setting goals so big, we're not just bringing one country together, we're bringing the world together to achieve them. And I think that's extraordinary. All right, next slide. So my path was, as Madison was saying, I joined the Royal Canadian Air Force, became a fighter pilot, and then the Canadian Space Agency was looking for new astronauts in 2008. I applied, And that's my friend David St. Jacques and I were accepted, and we moved down to Houston, Texas, and we started training with the NASA Astronaut Corps. Next slide. And now I'm part of an Astronaut Corps of 4 in Canada, and all of us work hand in hand. I live in Houston. I work at the Johnson Space Center every day, and we just work together to enable human space exploration. Next slide. One of the things that we're always working on is the International Space Station. And so right now, while we're chatting, there are 7 human beings on board the International Space Station. Yesterday, there were 10. 3 of them came back safely last night and landed in the steppes of Kazakhstan, so that's always good when you see your friends safely make it back to Earth. But this is an extraordinary example of human collaboration. The International Space Station was built, maintained, and leveraged for science by the United States, Russia, Canada, Japan, and the European Space Agency, which is comprised of many different countries. Arguably, this is one of our biggest technical accomplishments of humanity. It's an extraordinary challenge to put something like this together in space and operate it. And now we've had humans on board the space station. This is our 24th year of continuous human presence aboard the International Space Station. So it's a huge accomplishment. Next slide. But again, it's about collaboration and leadership to bring people together. And so if you want to be a member of this, you have to bring real value. And so Canada, we developed Canadarm1 for the space shuttle. Now we've developed Canadarm2, which you see here for the International Space Station. And that is why an astronaut like me can fly with our American colleagues to space, because of these contributions. All right, next slide. So that's what's going on in the International Space Station. Sorry, these slides are in Canadian because usually I'm giving the presentations in Canada, so they're in the kilometers, but I'll try to convert. The International Space Station is about 250 miles above the surface of the planet. And to go to the moon, we have to go about 1,000 times further. So that's why this starts to get really hard when you start to talk about the technology, the rockets, how much energy you need to get out there and get back. And the Artemis program is not just about going back to the moon. It is about using the moon to enable us to go to Mars. And Mars is another 1,000 times further than the moon. And you'll see in there in minutes, that's in Canadian and American, that is the communications delay. So if I was on Earth and this young man in the front row was on Mars, and I wanted to send a message to him, depending on where our 2 orbits are, it would take between 6 and 44 minutes for my message to get to him. And then I'd have to wait another 6 to 44 minutes for his answer to get back to me. And so it just gives you an idea how far Mars is from Earth and how big this problem set is for us. And why, one of the biggest aspects is figuring out how to get the world to work together on these things and create solutions to enable that kind of exploration. Next slide. So we had to build a bigger rocket to go back to the moon, and this is the SLS rocket, the Space Launch System. This is in Florida, the Kennedy Space Center. And next slide. This is what it looked like when it blasted off. Okay, so that was Artemis 1. I was very fortunate to watch it. It was louder than that, a lot louder. The next time we fly that rocket, I'm going to be sitting on top of that with Reed, Christina, and Victor, and that's super exciting. A little bit scary, but super exciting. And so I just can't even imagine what it's going to be like to ride that thing. It is a big, rumbly rocket. Look, when that thing goes, you really feel it. It's an emotional experience just being at the Cape and watching it. It's so powerful. So super excited to do that. A little bit about our mission profile. So we'll launch out of Florida. We'll fly around the Earth once in low Earth orbit, and that'll take about an hour and a half. And we'll do some very quick checkouts of the vehicle to make sure it's working, because we've never flown humans on it before. So we just want to make sure that we think we can survive another day. And if all that is good, we'll burn our engines again and we'll go out into a really highly elliptical orbit, which means we'll go really far from Earth, about 38,000 miles away. Remember, the space station's at 250. We're going to go to 38,000, so it's a lot further. And that'll take us a day, and that gives us enough time to check out the entire capsule, to make sure that we stress all the systems, that the life support systems are working, that the manual controls are working. If we have a problem in that first day, we can just come back at the end of it if we need to. But once we're convinced the capsule is good, then we're going to take it out around the moon and bring it back, and that'll take about 8 more days. So a total mission day or duration of about 9 days. And our job in Artemis 2 is simply to test this capsule to make sure it's ready to take humans to the surface of the moon on the future Artemis missions. Next slide. So we're just a stepping stone along the way. This is the crew and I checking out our capsule. This was in the summer. It's actually a lot further along now. But this is the Orion capsule that we'll actually be flying in. Next slide. This is what it looks like inside. This is our simulator in Houston. This is Victor and I doing some training on operating it. Next slide. We've done some medical training together as a crew, because if something goes wrong and we're in deep space, we can't just turn around and come home. We have to actually deal with it for that whole, once we leave Earth, we got 8 days and we have to ride it out. And so if anything comes up, it'll be us that has to deal with it and help one another out, with the support of mission control, of course, but we'll have to do any procedures, etc. Next slide. This is a dress rehearsal we did at the Cape for launch day. So we slept in the quarantine facility there, got up, had our last breakfast before launch, got suited up, walked out of the quarantine building where all the media always is and your family is there. So I had like a fake family standing there, and I was waving goodbye to my family. And then out to the launch pad in the next slide. No rocket there, but we rehearse all these things. It's not just us practicing, it's the entire team practicing every single thing that they're going to do on that day of launch. We have another one of these rehearsals coming up in a month. Next slide. This is us strapping into one of the mocked up capsules. We were training on return to Earth. We will land in the Pacific Ocean, ideally, if we're on target. The U.S. Navy will come and get us, ideally, but if we land in the wrong spot, we might be on our own for a while, so we have to practice our survival skills and how we're going to survive out in the ocean alone if we have to. Next slide. This is an exercise we did with the U.S. Navy, so actually got in a capsule out in the ocean. U.S. Navy showed up to rescue us. Once they get us in that raft, they lift us up in a helicopter, and then they take us back to the ship where we meet the medical personnel. And then next slide. This is the ship recovering the capsule. So we've already done all these exercises, so we know what we're doing and we can safely get back to Earth. Next slide. Some other training. This was in Labrador, Canada. So on the surface of the moon, we have a rock type called anorthosite. It's kind of like granite. It's very prevalent on the moon, especially on the South Pole, where we want to go, but is very rare on Earth. And there's a special place in Labrador, Canada, where there's a lot of this anorthosite, and it's actually been impacted by a meteor. And so there's a big crater there. And so we went there. This is Jenny. Jenny's actually my backup. So when I showed you that picture of 4 Canadian astronauts, Jenny's training alongside us, and she is my backup. If I can't go for some reason, Jenny will go. And we're training with, this is Dr. Rosinski, a geologist in Canada. And we had other members of the crew. Christina was there with us as well. And we're just getting this geology training ready for future astronauts who will actually collect samples from the moon. Next slide. So obviously we went to the moon in the Apollo program. We brought back rocks. We learned a lot from them. We're still studying them today. But the more we study them, the more questions we have. And so going back to the moon, we hope to unravel more mysteries of our solar system. But we also want to test out technologies that will help us get to Mars. Since Mars is so far, it becomes a big logistical challenge. And so growing food in space is going to be a big part of our strategy to get to Mars. And so we want to learn to grow food on the moon. But we also see some huge synergies with the challenges on Earth. So as we eclipse 8 billion people on the planet, and we start to put more and more pressure on our resources on the planet, being able to grow food in remote regions of Earth or where there's climate challenges like the Canadian Arctic is going to be very, very important for our future here. And so we see a real synergy between some of the basic needs technologies of space exploration and those growing challenges on the planet. So eventually we envision ourselves building bases on the moon. We are already next slide, we're already working on building the Gateway space station around the moon. The reason I am going on Artemis 2 is because Canada is building a third generation of Canadarm, so Canadarm3 for this Gateway space station. So this is another international collaborative part of the Artemis program. Next slide. And if you want to get to the surface of the moon, you'll need a lunar lander. So on our mission, we won't have a lander. So if we land on the moon, we are out of luck. We'll be staying. But in the future, we plan to have a lunar lander. We're building 2 of them. Blue Origin's building one, SpaceX is building the other with NASA. And this is called Starship. And I just wanted to show you a little bit about Starship. So look at the bottom. Can you folks see the little astronauts? This is a drawing, a graphic, but can you see these astronauts down here? No lazing me, Annie. Anyway, there's astronauts down there. That's like a lunar rover about the size of an RV coming down that elevator system. So this is a huge rocket. And next slide, here's a test version of the actual Starship. This is a real life photo, and there's a person standing underneath the rocket in that photo, just to give you an idea of the size of this. And the reason I wanted to share with you a little bit about Starship and how it's been going is because I think it is a good analog for how we approach problems in our own lives. So SpaceX has been taking what they call a rapid iterative approach. They have a concept, they build it, and they try it. And they don't expect it to succeed. In fact, they know it will most likely fail. But once they see what fails, then they correct that and they try it again. And in our lives, it's the same thing. When we set big goals, about the only thing I can guarantee you is that you will face big challenges and you will probably fail along the way. And success it comes from people who dig in and just keep pushing through that, to surround themselves with others to help them take on those challenges. So I'm going to show you a video of some of the challenges that SpaceX faced in trying to figure out how to land this rocket called Starship. Because it has to be able to land on the moon, but it also needs to be able to land on Earth so that they can reuse it and refuel it. And so there's nobody gets hurt in this video. There's nobody on board. Sometimes I forget to tell the audience, and then I hear the, no, nobody gets hurt in this video. But here is the path to getting Starship to work. So you can play the video, Andy. Isn't that incredible? Yeah, we should clap. Yeah, it's extraordinary. It's really hard to do what you just witnessed. And in life, there are lots of critics. There are lots of people who could point at that and say along the way that that design doesn't work, that it can't be done. And that is what you will face in your life. There are people that will tear you down. And what you need to focus on is, remember, surrounding yourself with people who will support you in your goals. Because anything is truly achievable. If you know where you're trying to get, you surround yourselves with the people that will help you get there by sharing your goals with them. And that's what we're doing in the space program. We are setting goals so big, we're bringing people together from around the world to achieve them, to do things like this, to send humans out to the moon. Next slide. As in Artemis 2, as we fly out to the moon, we'll fly around the far side of the moon, and this is what we'll witness. An Earthrise. And it'll be an extraordinary and privileged opportunity to witness this. but we'll also be able to photograph it again and take videos of it and share it back to the planet. And while Artemis 2 is not going to solve all of the challenges that we have on the planet, it is going to provide an example of the extraordinary things that people like you and I can achieve when we collaborate and come together to create solutions. Next slide. And we hope that even for just a moment during the Artemis 2 mission, that people will see these images and they will stop and they will be reminded that we're all on this planet together, that we could do a lot better as a human race of collaborating, creating solutions as opposed to destroying, and that is how we will successfully thrive on this planet and take on the big challenges that are ahead for us. Thank you. All right, so we've got some time for questions. So there's microphones here at the front, and I invite you to just come on forward and fire away. I'll try and answer them. Yeah, you want to go?
When you're going through the training and stuff, what does it feel like to have like no gravity?
Oh,
Is that,
yeah.
is it like, do you feel like you're in water? Do you feel like you're skydiving, or what does it feel like?
Yeah, great question. So in microgravity training, we don't get to do a lot of it. There are two ways we do microgravity training. We have a big pool, and something we have to practice a lot is spacewalks, because spacewalks are really, really hard. They're physically hard and they're mentally challenging. And so you have to practice it a lot, because they're also very dangerous. And so, but you're in a huge spacesuit when you do a spacewalk, and the spacesuit weighs like 400 pounds. And so if you put it on in gravity and you try to practice in it, it's really hard. And so what we do is we put it in this big pool and we make it neutrally buoyant in the water column. So we add foam and weights to it so that it floats as if it's in microgravity. Now you don't feel like you're in microgravity in there because you are in gravity, you just fall to the bottom of the suit. If you flip the suit upside down in the pool, you're resting on your shoulders, it's uncomfortable, the blood's flowing to your head. So you don't feel like you're in microgravity. But we do a lot of that training and it's very, very helpful. The other way we do it, and this is more closer to your question, we have an airplane, and you get in the back of a big airplane. It's like a passenger airplane, but there's no seats in it. And the pilot flies the airplane along, and then they pull the nose up into the sky, and then they push it down, and for about 20 seconds while it's going over the top like that, it's kind of like a roller coaster, you feel weightless, and you're flying around in the airplane, and it's crazy fun. Like, I don't have the word. Like, it's so much fun. Like, if you take a picture of somebody doing this, they have a huge smile. Unless they're vomiting, but then as soon as they're done vomiting, they're back to smiling because it is just that much fun to do it. But it's only 20 seconds at a time. And I've only done it twice, and I probably won't ever do it again. It's not something we need to practice. You know, once we get to space, you just figure it out. You're floating around. Oh, but what does it feel like? Have you ever been on a roller coaster where you go over the top and your tummy tickles? That only lasts for, half a second, and then it just feels normal, but very free. Like you don't really feel anything. You're just super comfortable, and you have a huge smile. Comes with it. Yeah. Yep. And come to the mics if you have questions, please.
How do you get to the space station?
Yeah. How do you get to the space station? Well, we need a rocket. I'll wait for you to sit down so you can hear the answer. Sometimes we ask the questions and then we forget to listen to the answers. So how do we get to the space station? Well, you have to fly in a big rocket. And it only takes you could get to the space station in about 9 minutes. But the thing is, you have to get from going 0 miles per hour to 18,500 miles an hour. So that takes about 9 minutes in a rocket to get to those speeds. And then you're in space. And then all you have to do is dock to the space station. So typically when we really go, we spend about 3 hours getting there, just so we can kind of slow things down and make sure that we don't run into the space station. So we enter into a lower orbit, then we take our time, we check everything out, and then we go up and up and up and eventually connect to the space station. All right.
So I understand this is the first woman that's going to the moon?
Yeah.
So how does that look different are they studying the physiology different? And you talked about synergy, will that come down to mainstream healthcare for women, do you think? Will that have an impact?
I don't want to oversell it. For sure, a lot of our human research is being done on the International Space Station, and so we've had women flying there for a long time, and we've been collecting data on all of the astronauts, and so we do have what kind of feels like a lot of data, but the end number is really small, if you know what I mean. There's not a lot of people in these studies because we only fly, about 14 people in space a year to collect data on. But I mean, the answer is, do we need? I think okay. Where do I go with this? My wife is a physician, and she's an obstetrician gynecologist, and so I have been well indoctrinated in the lack of medical evidence for women, how we are behind in studying the specific differences with women. And so I think that's sort of where your question is going. I think any professional in the business today understands that there are differences between the two bodies, that they need more emphasis on that study. So we collect data on everybody that flies equally, and it's openly available. It's not personalized data, but it's anonymous data, but people can apply to have access to that data to conduct studies, and that's our endeavor anyway. Does that answer it, or did I? Yeah?
Thank you.
Let's go back to this mic.
Like, how do you brush your teeth or like put toothpaste on a toothbrush?
Yeah. So toothpaste and a toothbrush are sticky, right? Like if you put your toothpaste on the toothbrush and you just kind of push it in a little bit, you could hold it upside down and it would stay there, right? Except when it doesn't. Sometimes it falls off. But usually it'll stay there. Well, it's the same in space. Even though there's no gravity, as long as you kind of paste it on your toothbrush, it'll stay there. And then you just brush your teeth like normal, except there's no sink to spit in. And so you have to use a bag of water if you want to rinse with water, and then spit that water into a towel. Just let the towel absorb it. And then what we do on Artemis, we don't have this capability, not yet. But on Space Station, we recycle all our water. So what we do is we hang our towel up, and we let it air dry. So that means that water goes back into the air. And then the cooling systems of the space station, that water gets absorbed back out like an air conditioner. And we collect that condensation, and we collect our urine, and we put it through a recycling machine, and we drink it again and again. We call it yesterday's coffee today, and we just keep drinking the same water over and over again. So it's a really cool technology. Yes?
So what's the hardest part of training for space to be an astronaut?
What's the hardest part of training? I think the real challenge is just how many things you have to train in. There's so many different aspects. And so it can look pretty daunting when you look at all the different things you have to learn. And the only reason that we're able to do it is because we have a pretty cool team of people that support us. And so I can't memorize, I'm not capable of memorizing everything that people teach me. So what I have to do is filter the information. So sort of like you go to class and you listen to the information, hopefully you make some notes and you take some notes about what's important and that what you're going to try to memorize when you get to the test and use. And that's kind of what I'm doing as an astronaut. I'm listening to all these experts who know absolutely everything about their specialty, and I'm trying to pick out the things and sort them into categories of things that will help me in space, things that I don't have to remember, I can rely on the ground to tell me, and then the things that will kill me or my friends. And like those ones I pay particular attention to, and I create little cheat sheets. Do these things or don't do these things so you don't kill anybody. Make sense? That's probably the biggest challenge. Okay.
What if you get like homesick on a rocket ship?
Yeah, what if you get homesick? So absolutely. So I'm only going to be gone 9 days, so it won't be too bad. But a lot of my friends are on the space station for 6 months. So the 3 people that came home last night, well, actually, last night was kind of unique. But one of them had been there for well over 6 months on her mission. And so we have to, in order to overcome our homesickness, we call home. So we can do video conferences. So sometimes my friends will call me from the International Space Station, and I'll be able to see them on my phone, and we can have a little conversation, and they call their families and their loved ones, and that's how we stay in touch. Yeah.
Does it get cramped when you're in the small shuttle for all 9 days? Does it like get really cramped?
Yeah, I haven't done it yet, but I think it's going to. What do you think? You think it'll be kind of cramped?
Probably.
Yeah. So Matt, our capsule is about the size of a minivan inside, and there'll be 4 of us in there. And once we get to space, we'll get rid of the seats. We don't need them anymore. They kind of collapse down out of the way. We'll get rid of the seats, and we'll have a little bit more room, and we can kind of stretch out. And there'll be enough room for us all to like stretch out and sleep in different places. And you're just floating around, so you can make better use of space. But imagine going car camping in a minivan for 9 days and never getting out. That's what it's going to be like. So yeah, I think when we hit the Pacific Ocean on day 9, we'd be like, yep, I'm ready. Pop the hatch. Let's go. All right.
What does breaking through the atmosphere feels like?
Okay, so I haven't experienced it, but I was watching the video of Artemis 1 coming back recently. When we come back from the moon, we'll be going 39 times the speed of sound, so Mach 39. It's really fast. And when you watch it in the videos, these are online on YouTube. You can look them up. Just look for Artemis 1 reentry. You'll be able to find it. And when I see it in the simulator, it is really cool. Like when you are coming back towards the Earth at Mach 39, like you know you're moving. You can see it. The Earth is getting big fast, and it looks really, really cool. It's going to be extraordinary to see it for real. And then when you hit the Earth's atmosphere, that starts at about 400,000 kilometers. So that'd be like 250 miles, something, or 250,000 feet, sorry. No, I got that wrong. It's 400,000 feet. That's when entry interface starts. That's when we start to hit the atmosphere. And then you start to see little like streamers of glowing red coming out off of the heat shield. And then it gets really intense. It looks like you're in a fireball. And it gets louder, like the air. You know, like when you're driving in a car and you hear the wind noise, you start to hear that. You can hear it in the video recording. And then you hear the jets, like the motors of the capsule firing, and they make these sounds like poof, poof, poof. And that's trying to keep the capsule stable as you're coming through the atmosphere. So it actually sounds and looks really, really cool. Like if you were on an amusement park ride, you'd be like, this is a really good ride. Oh, and then I should say, then when you get down into the atmosphere, you start to feel the G-forces. And so you have to decelerate from Mach 39 to close to 0 before you hit the ocean. And so you start to feel G-forces that are pushing you into your seat. So have any of you ever been to like a fair where you get in that like UFO looking thing where you're on the wall and it spins around and it lifts you up? When you're on that ride, you're probably feeling about 2 times the force of gravity on that ride. And we're going to be feeling, depending on our entry profile, somewhere between 5 and 8 times the force of gravity while we're coming back through the atmosphere. All right.
Have you ever seen an alien?
Have you? I have not seen an alien. Some of you are too young to know what X-Files is, but I used to watch X-Files, and it was a show about aliens, and I loved it because I was like the guy on the show. I want to believe, like I would love to think that aliens exist and that we could, talk with them and learn from them. But my personal belief is aliens are not visiting us here today, but they must exist somewhere in the universe. The universe is enormous. I love to tell explain a little example of why it is so hard to look for alien life in the universe, okay? So just bear with me for a second. So we live in which galaxy? What galaxy are we in? Milky Way galaxy. All right. And in our galaxy are a couple 100 billion stars, give or take. It's a lot. And then the closest neighboring galaxy is Andromeda. And Andromeda is 2.5 million light years away. So that's a long way away. And that's our closest neighboring galaxy. There's like a couple trillion galaxies out there, but the closest one to ours is Andromeda, 2.5 million light years away. That means if you were in Andromeda and I sent you a message, it would take 2.5 million years to get to you. So now that you know that it's really far away and information and light takes that long to get here, imagine that there's this amazing alien civilization in Andromeda, and they have the coolest telescope ever, and they are looking at us right now on planet Earth. And they're like, I wonder if there's people on planet Earth. What are they seeing? They are seeing us 2.5 million years ago. Are we here? No. We're not here. And so the whole point is even though it might be out there, that's our closest neighboring galaxy. If there's life in any of those galaxies, they would have had to have been there millions of years ago in order for us to be able to even hear from them or see them. So that's why it's hard to find alien life. But it doesn't mean they're not there. All right.
Do you think that the solar eclipse has anything to do with an earthquake that happened in New York City?
Do I think the eclipse has anything to do with an earthquake in New York City? No, I don't think so. Because nothing has really changed. Like what's happening, the only thing that is happening here is that the moon is passing directly in front of the sun from our perspective. But the moon isn't doing anything different than it always does. It goes around the planet once every how many days? 28 days, right? It just is always going around planet Earth. And we are always going around the sun. And so the moon does pull on the Earth, and that's why we have tides. You know what I mean by tides? How the ocean gets higher and lower. So the moon does pull on the water, but it's doing that all the time. So there's nothing new here. It just happens to be a very special day where it all lines up. All right.
How many people can be on the International Space Station at one time?
There's no specific limit. I think the most we've had up there, is 13 at once. I'm not 100% sure, but it was roughly 13. Typically, right now, we get up to, 13 when we are handing over between vehicles. Yeah, we can get up to that many. But there's lots of room up there. The problem is like how many people can we have space to sleep? How much water can we recycle? How much carbon dioxide can we pull out of the air? And so we're about at our limit, probably around 13 right now. All right.
Light can travel insanely fast, but like things that are far away, how can light affect time?
Well, okay. Well, that's an easy one. How can light affect time? So I was just giving you an example about how far our closest neighboring galaxy is and the fact it takes 2.5 million years for light to get here from there. And so that sort of affects time because things that are going on there we won't know about for 2.5 million years. So that does affect time. The other thing that you might be thinking about is relativity, general relativity. Thanks to Einstein, we know of something called time dilation, and that is the faster you travel, the slower time passes. So let's say you and I, how old are you now?
10.
You're 10, I'm 48. So let's say we put you in a rocket and we send you off to Andromeda at close to the speed of light. And then when you get back to Earth from your trip, maybe you don't go all the way to Andromeda because it's just too far to go, but you go really fast for a while and then you come back. I might be 49, but you might be, well, let's say I'm 50 and you'll be 11. So I got 2 years older, but you would only get 1 year older because you were traveling faster, close to the speed of light. That's a pretty crazy thing to think of. But we have actually proved this as true by flying really accurate clocks in space. So we take 2 clocks, we leave one on Earth, we fly one to space. It travels pretty fast, not anywhere near the speed of light, but it travels pretty fast. And when it gets back, it has ticked less than the clock on the ground. So time dilation is true, but we don't travel anywhere near the time or speed of light, so it doesn't really affect us yet. But someday it might.
So what does it feel like when you're blasting off and coming back at the same time?
Well, the best way I could show you is if I came down there and I grabbed you and I shook you like this.
No,
and then for coming back, I would put you on the floor and I would sit on your chest. And I would make it feel heavy on your chest because that's what the G-forces feel like. It feels like somebody's pushing on your chest.
Like how much pressure will you be in space? You're coming down, and how much will you going when you get to the moon? How much pressure is on you?
How much pressure? Well, I think you mean gravity, like gravity. Like,
yeah.
So right now you're at 1 times the force of gravity here on Earth. When we go to space, we'll be about 4 times the force of gravity on our launch. On our way back, we'll be about somewhere between 5 and 8, depends, times the force of gravity. So that's going to feel pretty heavy. And when we're flying around the moon, we'll have zero. We'll be floating as if we'll just be floating in space. We won't feel any gravity at all.
Like a flying bee?
Like a flying bee. Yep, that's it. Yeah.
How do you control the spaceship?
Yeah, how do we control the spaceship? So we have like a joystick in there. We have two like hand controllers, one for our left hand, one for our right hand. And on our vehicle, we have things called thrusters. They're little engines, and they fire pulses, kind of like, almost like puffs of air. They're fuel, but like, and if you want to turn the spacecraft, you fire the thrusters on one position, and it sort of rotates the spacecraft. And then when you get to where you want to be, you fire the other one, and it stops you. And so you just constantly fire these thrusters to position your spacecraft.
How do you know where you're going in the spaceship?
Yeah, how do we navigate in space? It depends. So when we are in low Earth orbit, we use GPS. Why wouldn't we? It works in low Earth orbit. But as soon as we start to get far away from Earth, GPS doesn't work anymore. GPS only points down towards the Earth. So once we leave that, we have to rely on a few things. We have something called gyros. And so they keep track. They feel every movement we have. And so they know how fast we're going and in what direction. And so we can constantly do math. You add up where you were to what you just felt, and it tells you where you are. But it's not perfectly accurate, so then we have to update our gyros. And we do that either by looking at the stars. So we have a special computer that looks at the star maps and figures out where we are. Or Earth can tell us where we are. So Mission Control can use radio signals, like a radar essentially, to figure out where we are and tell us where we are. And then they send it to us. Yes, over here.
How do you eat when you're in space? Oh my God, I sounded too loud.
How do you eat when you're in space? Well, same way you and I eat. Everything works normal, so like you can swallow just like normal, but we have to bring all our food. We don't have a kitchen on our spacecraft, and so what we do is we bring pre-packaged food, and a lot of it has been dehydrated. So it's all dried out, and it's in these little clear pouches, and then what we do is we add water, and it rehydrates, and then we just cut it open with scissors, and we eat it. And that's most of the food. Some of the food is just ready to eat. We just warm it up a little bit, like with a little suitcase warmer, like a briefcase. And it ggets warm in there, almost like a little mini oven. And we can put them in there and warm them up, and then just open them and eat them. For any of the drinks, we have these little bags, and they fly with no water in them. We add water in space, and then we just drink out of a straw. All right. Okay, back over there.
How do you take off?
How do we take off from Earth? Did you see that rocket I showed in the video, the big one? That's the rocket I'm going to ride in. So we built that big rocket. We're building the second one right now. And once it's all ready, we climb into the top, into the little tiny capsule at the very top. The four of us, we strap into our seats. They fill it up with fuel, and we light that thing, and away we go.
How come you did training in the ocean for space when the ocean and the space are different things?
Yeah, so why practice in the ocean? It's a great question. So when we come back from the moon, we have to land somewhere on Earth. And our capsule is designed to land in water because it's safer for everybody on the ground. We're coming back all the way from the moon. If we don't land in the right spot, we don't want to land on your house. And so we decided to land in the Pacific Ocean because it's a pretty big target to hit. So that gives us some room for error, especially while we're getting to know this capsule and how it flies. So landing in the Pacific Ocean is a safe place for us to land. And once we get down close to the ocean, our parachutes will open, and then we'll coast down and land in the ocean. That's why we had to practice, because that's where we'll be at the end.
Why do you go to space? That sounds dangerous.
Yeah. Smartest person in the room right there. I think, I've just kind of accepted that astronauts must have a screw loose, if you know what I mean by that. You must be missing some part of your brain, because I think it is a little bit dangerous, but we feel like it's worth the risk. Humans have always done risky things to explore. I mean, you have to imagine, in the beginning, however humanity happened, eventually we spread out over the planet. And that's some pretty incredible explorers who did that. Think about the indigenous populations that somehow made it to North America. We think over an ice bridge between Russia and Alaska, and they managed to explore all of this by foot. I mean, it's extraordinary. These were extraordinary explorers. Humanity has always done this. And I don't know what it is, but like inside of us, some of us want to go, some of us just want to work on the problem, but it seems to bring out the best in humanity. You should see the people I work with at NASA, the Canadian Space Agency. I mean, these people are a dog with a bone. They are inspired. They want to solve problems. The harder the challenge, the harder they want to work. It's really extraordinary to see the impacts of exploration on people. Could we solve problems on the planet without exploration? We definitely could. But from my perspective, by pushing humanity with exploration, we bring some of the craziest solutions to bear on the planet, and it's worth it. Yeah.
Are you allowed to bring stuff from like your house to space?
Yeah, can we bring stuff with us? On the International Space Station, we have a lot more ability to bring lots with us, so we would usually give, like each astronaut would have like a bag like this of personal things that they want to bring that are important and special for them. On Artemis, we're much more limited by mass and space available and volume, so we're not sure how much we can bring, but I'll be able to bring a few things, like maybe an envelope, like a big envelope full of things. I have, married, I have 3 kids, and I gave them each a little pendant for Christmas that I'm going to fly on my mission for them. So that's something I know I'm going to fly, but I'm still figuring out the rest.
Does time feel faster or slower in space?
Time feels exactly the same in space. It doesn't feel any different when you're up there. It just feels like a regular old day with respect to time. But the one thing that is very different is the sun cycle. So here, the sun rises and sets every 12 hours roughly. But in space, the sun is completely different. So if you're on the International Space Station and you're orbiting the Earth, you actually see a sunrise and a sunset every 45 minutes, one or the other. You see either a sunrise or a sunset every 45 minutes on the space station. So that's very different. If you're looking out the window, it makes your body feel like the time is going quickly, I suppose. For our mission, once we leave Earth, we'll be in the sunlight the entire time, except for when we go around one side of the moon. At some point, we'll be shadowed from the sun by the moon. All right. Yeah.
Is the moon made of cheese?
What do you think?
No.
You're right. It's not made of cheese. It's made of the same. It's actually made of Earth. We're pretty sure, it's actually kind of neat. We are pretty sure, not 100% sure, but we are pretty sure that the Earth was formed by a big object hitting Earth. We think something about the size of Mars hit planet Earth in early days of the solar system. And the two collided, and out of that collision, it spit off a whole bunch of molten rock out into orbit. And that rock started to coalesce and come together and group together and form a new ball called the moon. And we think that's how the moon formed. And that explains why the moon does not have a core like Earth has, and doesn't have a magnetic field like the Earth, because it's, well, forget the magnetic field part, but it doesn't have a core because the two cores of those objects stayed in Earth. But the crust of Earth that got spit off became the moon. So the moon is made out of the Earth's crust, essentially. But we want to prove that.
I think I know how the moon was made. By when the asteroid hit Earth and extinct the dinosaurs, lots of rock formed and then it made the moon. The only satellite that wasn't formed by humans.
Well, that's true that happened. We think that happened to kill the dinosaurs, right? That something hit the Earth and changed the Earth's environment. We think the moon formed before that impact, but it's very similar to that one. But this is why we're very curious to go back to the moon. Sometimes we refer to the moon as the Rosetta Stone of the solar system because there's a lot of information there that has been stored away like a library that we can go and see the historical past of our solar system. And that's why we have some new things that we want to collect from the moon. Good questions.
Is it easy to fly in? Is it easy to fly a rocket ship with so many buttons?
Is it easy to fly a rocket ship with so many buttons? I would say it's not easy. The reason you can do it is because you practice, practice, practice. So I don't know, what's something that you've done that's hard? Have you learned what?
Yes.
Pardon?
Yes.
Yes, you've learned something that's hard. Like maybe you've played a sport. You ever play any sports? Play with a ball or anything like that?
No.
No? Okay, well, anything you learn at first usually seems hard. But when you practice it over and over and over again, you get good at it. And that's how we learn how to fly our rocket ship.
I think I know how to fly a rocket ship.
You do?
Yeah.
Well, are you going to apply to NASA when you get older? Perfect. That's great. Thank you.
We'll have time for 2 last questions.
Oh, okay. Sorry about that, folks. Okay.
How do you go to the bathroom in space?
Yeah, that's the classic question for sure. I've answered it at least once before. So in space, it's pretty similar, but we're missing one important thing for our toilet, and that is gravity. So on Earth, the way your toilet works is gravity's there, and gravity pulls the feces or the poop away from your body. In space, we have a toilet like that, but we have no gravity. And so we have to replace gravity with airflow. So we have a special fan that pulls everything down, just pulling the air down all the time, and that traps the feces or the poop down in the bottom of the toilet and keeps it in there. And then it just kind of gets wrapped up in a bag and stored. And then for the urine, we basically urinate or go pee into a vacuum tube almost, and that pulls the urine away. So it all works with suction, basically, airflow. Yes?
What does
Oh, you're back.
What does the engine of the rocket ship look like?
Too hard to go back to the picture. The engine of the rocket ship looks like a great big suction cup. You know what I mean by that? So like it's a great big like a cone coming out the back, and inside there is an explosion of fuel and oxidizer, which is like oxygen, and those two mix together and they're burning, and that pushes us up into space. All right, well, thank you everyone for your time today.
Can I ask some questions real quick? Okay. So, when you're in space, will the gamma rays be harder, and will they hit the spaceship more active than on Earth with the atmosphere blocking them?
Yeah. So will the radiation effects in space be more than they would be on Earth? And the answer is yes. It's not as much the atmosphere, although that's part of it, but the biggest thing that we'll be missing is the protection of the Earth's magnetic field. And so the Earth's magnetic field is what creates, that's why we see aurora borealis or northern lights or southern lights, is because the Earth's magnetic field is stopping all of that radiation and energy from penetrating in, and that protects us. And when we go to the moon, we will be outside of that protection, so we will get a much higher dose in any given day than we would on planet Earth.
And another question about the video. If you were to have a parachute on the top of the rocket, wouldn't it create drag and it would stop it from blasting like that on the ground? If it was to hit the ground too hard, the parachute could create drag to drag it down.
Oh yeah, that's exactly how we're going to land. We will come through the atmosphere. The atmosphere will slow us down most of the way, and then at the very end, 3 parachutes will open. I'm going to knock on some wood. And then we will land safely in the Pacific Ocean. So I just wanted to circle back quickly, for especially young people, but it applies to all of us. I still use it in my life today. It's really, really important to set goals in your life and share them with other people. And that is how you will accomplish the things that are important, and that is how you will share your gifts with the world. Thank you, everyone. I appreciate your time.